Well, welcome back to our class on system engineering. In this lecture, we're going to be talking about advanced development. And to give some perspective on where we are in the material, now we've gone into this next major section. So we talked in detail about the concept development and the foundations. Now we're getting into when we actually are creating something, we're actually getting into the manufacturing and the detailed engineering development. So for this lecture, we'll be focusing on the beginning of that process, and let's start to get into that material now. So first of all, we'll talk about reducing uncertainties. The advanced development phase is that part of the system development cycle in which the great majority of the uncertainties inherent in the selected system concept are resolved through analysis, simulation, development, and prototyping. The principal purpose of the advanced development phase is to reduce the potential risk in the development of a new complex system to a level where the functional design of all previously unproven subsystems and components have been validated. At its conclusion, the chances of discovering serious problems must be sufficiently low that full-scale engineering may be begun with confidence. This phase's primary objectives are to develop, where necessary, and to validate a sound technical approach to the system design and to demonstrate it to those who must authorize a full-scale development of the system. To accomplish this objective, the degree of definition of the system design and its description must be advanced from a system functional design to a physical system configuration consisting of proven components coupled with a design specification to serve as the basis for the full-scale engineering of the system. In most new complex systems, this calls for a very considerable maturing of the design of a number of components or subsystems. All ambiguities in the initial system requirements must be eliminated. And often some of the more optimistic design goals of the original concept of the system must be sufficiently curtailed. It should be noted that all new system developments do not have to go through a formal advanced development phase. If all major subsystems are directly derivable from proven predecessors or otherwise mature subsystems, and their characteristics can be reliably predicted, then the system development can proceed onto the engineering design phase, such as is the case with most new model automobiles, in which the great majority of components are directly related to those of previous models. In that case, such critical items as the airbag system, hybrid power, or autonomous operation may be individually built and tested in parallel with the engineering of the new model. Well, let's put this in context for where we are overall in this process of our development. So we want to consider the place of the advanced development phase in the system lifecycle. And so that's what we're showing in this figure. The advanced development phase marks a transition of the system development from the concept development to the engineering development stage. So that's seen as in the figure I'm showing here. It follows the concept definition phase from which it derives the inputs of the system, functional specification, and a defined system concept. Its outputs to the engineering design phase are system design specification and the validated development model. It thus converts the requirements of what the system is to do in a conceptual approach of the configuration into a specification of generally how the required functions are to be implemented in hardware and software. Other required outputs that aren't shown here include an updated work breakdown structure, WBS, a revised system engineering management plan, SEM, or its equivalent, and related planning documents. Additionally, the system architecture is updated to reflect changes to date. As noted before, this phase is especially critical in the development of complex systems that involve extensive use of advanced technology and not novel, unproven concepts. It may require several years of intensive development effort before the new features are sufficiently mature and well demonstrated to warrant initiating full-scale engineering. In addition, it may also be necessary to develop new manufacturing processes to support proposed new technology. In such cases, the advanced development phase is frequently contracted separately from the follow-on engineering. If at the other end of the spectrum, those systems that do not involve major technological advances over similar previous systems and hence require only a minor amount of development may not have a separately defined and managed advanced development phase. Instead, the corresponding work may be included in the front end of the engineering design phase. However, the task embodied in the translation of the system functional requirements into a system implementation concept and system level design specification must be accomplished prior to undertaking detailed engineering. Well, let's put the design materialization into where we're at in this development. So we have the advanced development phase materialization. We talked about the concept development. We walked through these phases in even more details than are shown here. Now we're in the advanced development. And so this table depicts the system materialization status during the advanced development phase. It is seen that the principal change in the system status is designated as validation of the soundness of the selected concept, validation of its partitioning into components, and validation of the functional allocation to the components and subcomponents levels. The focus of development in this phase is thus the definition of how the components will be built to implement their assigned functions. The manner in which these tasks are accomplished is the subject of the material in this lecture and in this chapter. Well, let's use this figure that we have talked about previously, but put it into the advanced development phase perspective. So thus we're talking about the system engineering method and how it is applied in advanced development. So the organization of what we're talking about this lecture and the corresponding chapter is arranged according to the 4 steps of the system engineering method, followed by a brief section that discusses risk reduction, a methodology used throughout system development, but is especially important in this phase. The principal activities during this phase in each of the 4 steps in the system engineering method as applied to those subsystems and components requiring development are briefly summarized here, and we're showing it in this figure as we go through that. So typical activities in each phase are listed here. If you go to the textbook, and I'll just give you a short synopsis. So first of all, the requirements analysis. What's done here is analyze the system functional specifications with regard to both their derivation from operational and performance requirements and the validity of their translation into subsystem and component functional requirements. Also, it deals with identifying components requiring development. For the functional analysis and design, deals with 2 things, analyzing the allocation of the functions to components and subcomponents, and identifying analogous functional elements in other systems. Plus, it does performing analysis and simulations to resolve outstanding performance issues. Next, for the prototype development, it deals with identifying issues of physical implementation involving unproven technology and determining the level of analysis, development, and test required to reduce risk to acceptable values. It also explores designing critical software programs. Plus, it deals with designing, developing, and building prototypes of critical components and subsystems. And finally, correcting deficiencies fed back from test and evaluation. Then for development testing, creating test plans and criteria for evaluating critical elements and developing, purchasing, and reserving special test equipment and facilities. It looks at conducting tests of critical components, evaluating results, and feeding back design deficiencies or excessively stringent requirements as necessary for correction, leading to a mature, validated system design. Agile system engineering approaches may be leveraged during this phase of system development by organizing the team to work within a defined scope and defined time frame. The entire team will have the understood goals and expectations for their specific capability through frequent meetings and interactions. Progress can be evaluated or help can be requested. This may assist the team to have the additional focus on the interfaces between components of the system and potentially raise additional integration and or testing issues before they are due to be developed. Next, we'll get into a discussion of requirements analysis. So as we stated before, the initial effort in the advanced development phase is mainly devoted to two areas. One, re-examining the validity of the system functional specifications developed in the following concept definition phase or following the concept definition phase. And two, identifying those components of the selected system concept that are not sufficiently mature for full-scale engineering, and which therefore should be further developed during the advanced development phase. Well, let's talk about some of these things specifically. And I've listed these in the middle down to the end of this chart. So for system functional specifications, in defining the preferred system concept in the concept definition phase, the system functions were allocated to the principal subsystems, and these were further broken down into functional elements. These functional design concepts were then embodied in the system specification document prepared as an input to the advanced development phase. The analysis of these specifications should take into account the circumstances under which the concept definition phase took place. If, as is frequently the case, it was performed in the space of a few months and with limited funding, and especially if it was done in a competitive environment, then the results should be viewed as preliminary and subject to modification and must be analyzed very thoroughly. Prior design decisions must be viewed with some skepticism until they are examined and demonstrated to be well-founded. This does not mean that these selected technical approaches should necessarily be changed, only that they should not be accepted without understanding their derivation. Then we get into requirements derivation. The key to understanding the significance and sensitivity of system functions specifications is to trace them back to their derivation from the system performance requirements. As an understanding is necessary to make the design decisions required for the physical implementation of the functions in hardware and software, the system lifecycle supports scenario should be revisited to identify functions necessary to sustain the different circumstances in which the system will be exposed during its pre-operational as well as its operational life. In addition, the requirements for compatibility, reliability, maintainability, and availability and environmental susceptibility should be examined, as well as those for operational performance. At this time, specifications concerning human system interfaces, issues, and safety are incorporated into the subsystem and component specifications. Sometimes requirements are frequently unstated, and others are immeasurable. For example, affordability and system growth potential are frequently not explicitly addressed. User interface requirements are often qualitative and not susceptible to measurement. The relationship of each of the above issues is to the functional design needed to be understood and documented. Well, let's next think about the relationship to operational requirements. If some system specification cannot be readily met, it is necessary to gain an even deeper understanding of their validity by tracing them back to one step further, namely to their relationship to the execution of the system's mission, that is, to the system operational requirements. This relationship is often lost in the early phases of system definition and needs to be recaptured to provide the system engineer with an informed rationale for dealing with problems that invariably arise during development. One of the means for gaining such understanding as well as for obtaining an appreciation of the operational factors beyond those formally stated is to develop contacts with prospective system users. Such contacts are not always available, but when they prove extremely valuable. Organizations that specialize in operational analysis and those that conduct system field evaluations are also valuable sources in many system areas. Involving the user as a team member during development should be considered where appropriate. Next, we want to be thinking about the relationship to the predecessor system. If the new system has a predecessor that fulfills a similar function as is usually the case, it is important to fully understand the areas of similarity and differences in how and why the new requirements differ from the old. This includes the understanding of the perceived deficiencies and of the predecessor system and how the new system is intended to eliminate them. The degree of benefit to be gained from the comparison, of course, depends on the accessibility of key personnel and records from the predecessor system development. However, at a minimum, the comparison should provide added confidence in the chosen approach or suggest alternatives to be explored. When key participants in the development are accessible, their advice with regard to potential problems and lessons learned can be invaluable. Finally, we want to be thinking about the identification of components requiring development. The principal purpose of advanced development phase has been stated as ensuring that all components of the system have been demonstrated to be ready for full-scale engineering. This means that the component design is sound and capable of being implemented without significant risk of functional or physical deficiencies that would require different approaches to satisfy the requirements. So this implies that the system components must be brought up to the level of maturity where all significant design issues have been resolved. The process that raises the level of maturity is called development, and therefore the advanced development phase consists largely of development efforts focused on those system components that have not previously been brought to the necessary level of proven performance. This in turn means that all components that are determined to be insufficiently mature for full-scale engineering would be further developed and their designs validated. Those components that are deemed to be sufficiently mature that they do not require development still need to be validated through analysis or test prior to their acceptance for engineering. Well, let's continue on with more specifics for this part of the component development. So first, assessment of the component maturity. The determination of whether or not a given component is sufficiently proven for full-scale engineering can only be made by comparing the components with analogous components that have been successfully engineered and produced. If not proven analogous components is similar to the new one, the comparison may often be made in two parts, functional and physical, by asking the questions: one, are the proven components that have very similar functionality and performance characteristics? And where significant differences exist, are they within the demonstrated performance boundaries of this type of a component? And second, are there existing components whose physical construction uses similar materials and architectures? Are the projected stresses, tolerances, safety, and lifetime characteristics within the demonstrated limits of similar existing components? If both of these questions are answered in the affirmative, a case may be made that the development is not necessary. However, An additional critical question is whether or not the functional interactions and physical interactions of the components with their operational environments are understood well enough not to require development and experimentation. The answer to this question depends on whether the difference between the proposed components design and those previously proven are reliable, predictable from known engineering relationships, or whether the relationships is too remote or too complicated to be predicted with assurance. A common example of the latter case has to do with human-machine interfaces, which are seldom well enough understood to obviate the need for experimental verification. Then we have the risk analysis. And so after identifying those system elements that require further development, the next step is to determine the appropriate nature and extent of such development. This is where system engineering knowledge and judgment are especially important, because these decisions involve a careful balance between the cost of a thorough development effort on the one hand and the risk inherent in sufficient development and consequent residual uncertainties on the other. Reference to the application of risk assessment to system development is contained in some of the material that we'll be talking about shortly, and this methodology is enlarged upon in the later part of the chapter and the later part of this lecture. Then we have development planning. It is clear from what we discussed just previous to this that the planning of the advanced development phase should be based on a component by component assessment of the maturity of the proposed system design to define, one, the specific character of the unproven design features, and two, the type of analysis, development, and test activities required to resolve the residual issues. In most new systems, the uncertainties are concentrated in a limited number of critical areas so that the development effort can be focused on those components deficient in design maturity. And then finally, in terms of the risk reduction budget, the result of the above analysis of the risk and definition of appropriate risk reduction effort should be incorporated into a detailed development plan to guide the analysis, development, and testing effort of the advanced development phase. In doing so, an essential step is to revise carefully the relative allocations of effort to the individual components or subsystems that are planned for development. Do the relative allocations correspond to an appropriate balance from the standpoint of potential gain to investment ratio? Is each allocation adequate to acquire the needed data? If, as is often the case, the available resources do not cover all the proposed effort, it is usually better to replace some of the most risky components with more conservative choices than to fail to validate their use in the system. Thus, the risk reduction and development plan should contain a risk mitigation budget broken down into the significant individual development efforts. Well, let's get into more details about new component development, and we'll have a couple examples here. First, we'll talk about unproven components, and we have the figure here that supports that. And then we'll talk about an alternative powered automobile and think of how that would come into play there. So this table illustrates the considerations we talked about just before this by listing several representative examples of hypothetical unproven components that are new functional or physical design approaches or new production methods. The first column indicates the relative maturity of the functional, physical, and production characteristics of the design approach. The second column is a bar graph representing the maturity of these three characteristics by the relative height of the three vertical bars. The third column shows the type of development that is usually appropriate to resolving the resulting issues of each of the new designs. And finally, the fourth column lists the particular characteristics to be validated. So these examples are, of course, very much simplified compared with what the factors that must be considered for an actual complex system, but they indicate the component by component analysis and planning that is associated with the advanced development process. So the table illustrates that components in a new system may have a variety of different types of unproven features, each requiring a development approach tailored to its specific character. The decisions are as to the choice of development strategies are the primary responsibilities of systems engineering. The subsequent three sections that we'll talk about here describes the application of each of the remaining steps of the system engineering method to the resolution of the above design issues. So we can see there's a design approach, maturity, development, and validation. And so we get a chance to be looking at these various types of components and see which one we might feel the most comfortable with. And so, well, let's go ahead and get into another example here. We'll be thinking about an alternative powered automobile. The development of an automobile that uses natural gas, electricity, or solar cells as fuel in place of gasoline offers an example of some of the principles discussed of what we talked about above. So this development has the dual objective of conforming to future strict auto pollution standards and fuel economy, while at the same time preserving all of the desirable characteristics of conventional modern automobiles, including affordability. Thus, it seeks to minimize the required changes in standard auto design by limiting them to the fuel system and its immediate interfaces. Other changes to the body, engine, and other components are kept to a minimum. The changes to the fuel subsystem, however, are considerable and also impact the design of various sections of the body. Storing a sufficient amount of natural gas or electrical power to obtain the desired travel distance between refueling, and also keeping the fuel storage or collection volume small enough, requiring gas storage pressures higher than those used in conventional storage cylinders, or adequate battery storage, weight, and space. To maximize safety, the container must be anchored to the frame so as to withstand severe rear-end impacts. The physical construction of the fuel container is a major departure from the conventional containers in its physical design and materials. Furthermore, the determination of its safety from explosion in case of collision is not derivable from engineering data, but must be established by experiment. The fuel control collection approaches or refill provisions will also be new designs. Thus, a substantial development effort will have to be undertaken to validate the design and probably will involve comparative testing of several design variations. In addition, such will depend on the full system perspective, including availability of numerous refill stations. The components that interface directly with the fuel system, such as the engine and the body structure, will also need to be tested in conjunction with the fuel container. Components not associated with the system element will require development, but must be examined to ensure that significant interactions are not overlooked. So this example illustrates a common case of a new system that differs from its predecessor in a major way, but one that is restricted to a few components. Now we'll get into a discussion on functional analysis and design. So let's first start out with this slide, and then we'll have a detailed chart that I'll get into some more details, which will come next. So because of the rapid advances of modern technology, a new system that is to be developed to replace an obsolescent current system will inevitably have performance requirements well beyond those of its predecessor. Moreover, in order for the new system to have a long, useful operational life in the face of further projected increases in the capability of competitive or opposing systems, The requirements will specifically specify that its performance more than meets the current needs, while the concept definition phase should have eliminated excessively risky approaches. These requirements will necessitate the application of the advanced development and therefore development of some advanced system elements. The increase in system performance frequently requires a significant increase in component complexity, as in many of today's automated computer-based systems. The means for achieving such projected extensions are often not reliably predictable by analytical or simulation methods and have to be determined experimentally. System elements involving dynamic behavior with feedback may be analyzed through simulation, but usually require the construction and testing of an experimental models to establish a firm basis for engineering. A common instance where system function may require development is where the user needs the environment and the environment are not well understood, as is often the case with decisions support and other complex automated systems. In such instances, the only sound approach is to build prototype components corresponding to the critical system elements and to test their susceptibility by experimentation. So in summary, these types of components that frequently require development are: one, components required to have an extended functional performance beyond previously demonstrated limits; two, components required to perform highly complex functions; and three, components whose interactions with their environment are imperfectly understood. So each of these are described in greater detail, and we'll get into that discussion here. So here we're showing a table of selected critical characteristics of system functional elements, and this is getting more in depth with a critical characterization of system elements. So, and we'll be walking through these topics here. So extended functional performance, the identification of system elements whose required performance may exceed demonstrated limits can be illustrated by reference to the set of functional system building blocks discussed earlier. So this table that we're showing, it lists 23 basic functions, elements grouped into 4 classes: signal, data, material, and energy. And so the color code gives you a sense of that. And so we've had those 4 classes discussed in some of our previous lectures and previous chapters. Each functional element has a number of key characteristics that define its functional capability. Most of these characteristics have limits established by the physical properties of their implementing technologies, and often by the basic interdependence between functions. A functional requirement for a new system that poses demands on a system element beyond its previously demonstrated limits signals the potential need for either a component development effort or reallocation of the requirement. So, so to illustrate this type of comparison, what we have here in the table, it lists the functional elements along with some of the characteristics that most often turn out to be critical in new systems. So the table represents the application of the system engineering approach to the analysis of system functional requirements and the identification of development objectives. And using system building blocks to identify functional elements requiring development, the first step is to relate each system element to its functional equivalent generic element, and then to compare the required performance with that of corresponding physical components whose capabilities have been demonstrated as part of the existing system. So given an appropriate correspondence, the next step is to see whether the difference between the required and existing elements can be compared quantitatively by establishing engineering relations so as to make a convincing case that the new element can be engineered with confidence on the basis of proven performance and straightforward engineering practice. When such a case cannot be made, it is necessary either to reduce the specified performance requirements to a level where it can be so adapted, or to plan a development and testing program to obtain the necessary engineering data. The process of identifying elements requiring development is often part of the process of risk identification or risk assessment. Risk assessment considers the likely effect of a given decision, in this case, the choice of a particular technical approach, or the success or failure of the overall objective. Thus, the utilization of unproven system components involves a degree of risk depending on the likelihood that the system will fail to meet its design goals. The risk is considerable, as when the element is both unproven and critical to overall system operation, then the element must be developed to a point where its performance may be demonstrated and validated. The subject of risk management we talked about in another chapter, and is encountered in all phases of this system life cycle. Well, next we'll talk about highly complex components. Consideration of the functional building blocks as system architectural components is also useful in identifying highly complex functions. Equally important is to identify complex interfaces and interactions, because elements of every moderate complexity may interact with one another in complicated ways. Interfaces are especially important because complexities internal to elements are likely to be detected and resolved during design, while problems resulting from interface complexities may not reveal themselves until integration testing, at which time changes required to make them operate properly are likely to be very costly in time and effort. The existence of excessively complicated interfaces is a sign of inappropriate system partitioning, and is the particular responsibility of the system engineer to discover and resolve. This concern is particularly important when several organizations are involved in the system development. In terms of specialty software, certain customized software components are inherently complex and hence sources of program risk and should be treated accordingly. 3 types of software in particular are especially difficult to analyze without prototyping. These are real-time software, 2 distributed processing, and 3 graphical user interface software. In real-time systems, the control of timing can be especially complicated, as when system interrupts occur at unpredictable times and with different priorities for servicing. In distributed software systems, the designer gives up a large degree of control over the location of system data and processing amount among network data processors and memories. This makes the course of system operation exceedingly difficult to analyze. In graphical user interfaces, their requirements are often incomplete and subject to change. Further, the very flexibility that makes such system useful is itself an invitation to complexity. Thus, the above special software modes, which have made computer systems so powerful and ubiquitous in today's information systems, inherently create complexities that must be resolved by highly disciplined design, extensive experimentation, and rigorous verification, including formal design reviews, code walkthroughs, and integration test. So we'll talk about it later in another chapter. And lecture is devoted to the subject of software engineering and its specific challenges. For dynamic system elements, another form of complexity that usually requires development and testing is inherent in closed-loop dynamic systems, such as used for automated controls. While these lend themselves to digital or analog simulation, they often involve complex and secondary effects that cannot be readily separated from their physical implementation. Thus, the great majority of such system elements must be built and tested to ensure that problems of overall system stability are well in hand. Well, let's next talk about ill-defined system environments. Poorly defined system environments and imprecise external interface requirements are also design issues that must be carefully examined and clarified. For example, a radar system designed to detect targets in the presence of clutter due to weather or surface returns is impossible to characterize in a well-defined fashion due to the great diversity of possible operational environmental conditions and the limited understanding of the physics of radar scattering by clutter and anomalous radar propagation. Similarly, space environments are difficult to understand and characterize due to the limited data available from past missions. The expense of placing systems into a space environment means testing and operational data are not as prevalent in atmospheric data. The operation of user interactive systems involves a human-machine interface, which is also inherently difficult to define. The parts of the system that display information to the user and then accept and respond to user inputs are often relatively uncomplicated physically, but are intrinsic logically. This complexity operates at several levels, sometimes beginning with the top level objective of the system, as in the conceptual design of the medical information system, where the need of the physicians, nurses, clerical staff, and others that interact with the system tend to not only ill-defined, but also highly variable and subject to argument. At lower levels, the form of the display, the format of the information access, portability, and means of data entry may all constitute system design issues that are not likely to be settled without extensive testing of alternatives. The design of automobile airbags represents another type of component with a complex environmental interface that has required extensive development. In this case, the conditions for actuating the airbag had to be explored very thoroughly to establish a range between excessively frequent and traumatic false alarms and assured responses to real collisions. The shape, size, and speed of inflation and subsequent deflation of the bag had to be provided maximum safety for the individuals with minimum chance for injury by the force of inflation of the bag. This example is representative of system environment interactions that can only be accurately defined experimentally. It illustrates a system component whose operational and functional performance cannot be separated from the physical implementation. So in terms of functional design, besides identifying the system elements required for further development, the functional design and integration of the total system and its functional elements must be completed during this phase. This is a necessary step to developing the system design specifications, which are a prerequisite to the start of the engineering design phase. So we have the functional and physical interfaces. Prior to the initiating full-scale engineering, it is especially important to ensure that all overall system functional partitioning is sound and will not require significant alteration in the engineering design phase. Before a major commitment is made to the detailed design of individual components, the proposed functional allocation to subsystem and components and their interactions must be carefully examined to ensure that a maximum degree of functional interdependence and minimum interface complexity have been achieved. This is necessary so that each component can be designed, built, tested, and assembled with other components without significant fitting or adjustment, not to mention adaptation. This examination must take into account the availability of test points at the interface for fault isolation and maintenance, environmental provisioning, opportunity for future growth with minimum change to the associated components and all other system components characteristics of a good product. The system functional and physical architectures are emphasized in this phase because the design should be sufficiently advanced to make sure judgment meanings, but is not as yet as so committed as to make modifications unduly time-consuming and expensive. Plus, there are software interfaces. And so previously we noted that many new software components are too complex to be validated only through analysis and need therefore to be designed and tested in this phase. Further, many hardware elements are controlled by or interface with software. Hence, as a general rule, it can be assumed that many, if not most, software system elements will have to be first designed and subsequently implemented in this phase of the system development. Then we have the use of simulation. Well, many of the things we just discussed require resolution by prototyping actual hardware and software. A number of others can be effectively explored by simulation. Some examples are dynamic elements, except for very high frequency dynamic effects. Most system dynamics can be simulated with adequate fidelity. The 6 degrees of freedom dynamics of aircraft or missiles can be explored in great detail. We can be using simulation for human machine interfaces. So user interfaces are control elements of most complex systems. The proper design requires the active participation of potential users in the design of the system elements. Such participants can best be obtained by providing a simulation of the interface early in the development and enhancing it as the experience accumulates. And for operational scenarios, operational systems are usually exposed to a variety of scenarios that impact the system in different ways. A simulation with valuable input conditions is valuable in modeling these different effects well before a system prototype or field test can be conducted. Okay, the textbook walks through an example with an aircraft design. That's one of the ones that we have been thinking about in terms of things we revisit in terms of general areas that could be applicable. But I'll leave it to you all that you can go to the textbook and read that.